Chapter 7, Quantum Mechanical Model of the Atom. Yeah, it's kind of a scary title. The good thing is we don't have to completely understand. I would like it if my computer would let me advance the slide. I don't know what that was about. Okay. Quantum mechanics had its beginnings back in the early 20th century. Before that, it was believed that all physical phenomena were deterministic. The present condition determines what's going to happen to that object in the future. But many famous scientists, some of whom you've probably heard of, like Einstein, working on information that they, that sentence really just didn't start well, so. Yeah. Okay, I'll just go with what's on the slide. So, work by many famous physicists discovered that for subatomic particles, the present condition does not determine the future condition. The present velocity, trajectory, and location of a very small particle does not determine where it will be in the future. So if you shoot an electron down a path and measure where it lands, and then you shoot a second electron down the path in exactly the same way, the second electron will most likely not land where the first electron did. What?
Even if you shot it at the same trajectory and speed and everything?
Yes, even if you shot it in exactly the same way. This is not how baseballs behave. You throw baseballs in the same way, identical baseballs, they go to the same place. Not electrons. That's disturbing, isn't it? It should be disturbing. I mean, this is not how things work. This is not how things that we can see work.
So just because a baseball isn't really affected by individual air atoms like gas atoms?
Well, even if you take into account friction from air, wind, and all those other things, for an electron, it doesn't matter.
So if you shot it in a vacuum, same trajectory?
You shoot an electron in a vacuum in exactly the same way, it will most likely not go to the same place.
Will it get close to it then?
It'll be in the vicinity, but it will not be the same like larger objects are. So let's move on. Hopefully, my computer is not behaving. So electrons are in a category called the absolutely small, or quantum world. Okay, the macroscopic world is things that we can see. My calculator, part of the macroscopic world, I can see it. There's also a microscopic world, things you can look at in biology lab under a microscope, right? You can't see them with your naked eye, but you can see them with a microscope. The quantum world is far smaller than that. When unobserved, absolutely small particles like electrons can be in two different states at the same time. This does not mean California and Nevada. Two different states of being at the same time. This is a very disturbing concept. An unobserved radioactive nucleus. You've heard of radioactivity. Radioactive nuclei decay by spitting out a small chunk of themselves. They emit alpha, beta particles or gamma rays. And you would think, well, that nucleus is either emitting a particle right now or it's not emitting a particle. But if we're not observing it, it is doing both at the same time.
Why do we say it's doing both at the same time?
Because it is doing both at the same time. It is simultaneously emitting a particle and not emitting a particle. And this is very disturbing. So let's try to get our minds around how small electrons are. So think of a speck of dust floating in the air. Tiny, right? We can see it, but just barely. So a single speck of dust has more electrons in it than all of the people that have ever lived on the earth put together. What? That's a lot of electrons. No, it has electrons.
So it has electricity kind of inside?
Well, electricity is the flow of electrons. But all matter is composed of atoms, and all atoms have electrons. So all matter has electrons. So that's, crazy small. We saw scanning tunneling microscope pictures of atoms, right? Very, very fuzzy pictures. That's the atom, okay? If the atom was the size of a football field, the nucleus would be the size of a pea on the 50-yard line. And what's inside the nucleus? Protons and neutrons. Those particles are 2,000 times larger than the electrons, right? So electrons, really small, really small. Directly observing electrons in the atom is not possible. They're just too small. And the other really annoying thing about electrons, because they're so small, is that when you observe it, it causes the behavior of the electron to change. This is a little bit like that annoying kid in school who, whenever the teacher's back was turned, was like torturing you, right? And the teacher turns around, oh, angel, right? They were getting you on the playground, they were getting you on the bus, right? The observation of the teacher changes their behavior. That's how electrons are. Even shining a light on it can change the behavior of an electron. So, we're going to look at a couple of videos here. Schrodinger's cat is a thought experiment. No cats were harmed. Okay, there was no actual cat. It was just a what if. And the idea, the point behind this thought experiment is to demonstrate how ridiculous the behavior of the quantumly small is, and that it does not translate into the behavior of the macroscopic world. So let's watch these videos.